area between curves, volume of solids of revolution, and volume of solids with known cross-sectional areas. So before we get started, let's take a look at some formulas that are going to be guiding our problem-solving process. So title it formulas. All right, first one has to do with area. So the area formula is basically the integral from a to b of the function on the top, let's call it f, minus the function on the bottom, let's call it g. It could be the function to the right or the function to the left. All right. How do we know the orientation? Well, dx basically indicates a top-down orientation. Function on the top minus the function on the bottom. In this case, the slice, the cross-sectional area of the rectangular region is going to be perpendicular to the x-axis. Or dy is a situation where you're looking at a function to the right minus a function to the left. Okay, in that case, your cross-section, your rectangular region will be pointing to the y-axis. Okay, with this orientation, g is less than f. Okay, either g is to the bottom of f or g is to the left of f. Now, volume is a little bit more intricate. Let's take a look at the formula for volume. So volume is the integral from is pi times the integral from a to b of the outer radius, big R square, minus the inner radius r square. Okay, that gives us the area of the washer, and then when we integrate from a to b, we can find the volume. Dx is when your radius is perpendicular to the x-axis or pointing to the x-axis, and then the y is when your radius is perpendicular or points to the y-axis. Now there are two scenarios here, depending on the orientation of your axis of rotation. So let's take a look at the two cases. The first one, pi times the integral from a to b. If you're looking at a top-down orientation where top-down or left-right, if the axis of rotation is less than the two functions, we're going to have the function on the top or to the right minus your axis of rotation square. This is big R square. Pi R square will help you find the area of the bigger disk, minus g minus a square. This is little r square. So pi times that square will give you the area of the inner disk, and then when you subtract these two areas, you get the area of the washer. Okay, so dx, if your radius is perpendicular to the x-axis, or dy, if your radius is perpendicular to the y-axis. All right. So this situation is applicable when a is smaller than both functions. Either it's at the bottom of g and f, or it's to the left of g and f. Okay? And then the other situation we have is pi times the integral from a to b of a minus f. This is big R. The difference here is a is bigger than both of the two functions. Okay, so a minus f square will give you the outer radius, minus a minus g square will give you the inner radius. Dx, if your slice is perpendicular to the x-axis, or your radius is perpendicular to the x-axis, or dy, if your slice is perpendicular to the y-axis. This orientation is applicable when f is less than g and g is less than a. It's like a reversal of the order here. Okay, I always like to put f at the end and then put g in the middle and then a at the other end. So this formula is applicable to revolution, solids generated as a result of revolution. Now, how about the volume of solids with known cross-sectional area? That's very straightforward. That one, the volume is simply going to be the integral from a to b of the cross-sectional area. It could be a of x or a of y, dependent. So it's dx if the base is perpendicular to the x-axis, or dy if the base of the area is perpendicular to the y-axis. So this is for cross-sectional area. Let's put that note there, cross-section. The only hard part with this last formula is finding the area of the cross-sectional area, because you have to make use of your geometry formulas to find the area. Okay. All right, let's take a look at problem number 1, the A part. It says let R be the shaded region bounded by the graph of y equals ln x and the line y equals x minus 2, as shown above. Find the area of R. Okay, so to find the area, it's good to use the formulas to guide our problem solving process. So the formula for area that we talked about earlier is the integral from a to b of f, the function on the top or to the right, minus g, the function on the bottom or to the left, dx or dy. Now here we have a situation where, regardless of how we cut it, our region, we're going to have one function constantly on top and one function constantly on the bottom, or one function constantly to the left and one function constantly to the right. So this one, since the problem is already in terms of x, we might as well slice in the x direction. Okay, so we're going to be going top down. That's what our slicing is going to be. So let's go ahead and put in the intersection. You can use your calculator to do this. Hopefully you know how to find the points of intersection using your calculator. If you don't, I have a lot of tutorials that go over that in detail. So you just find the points of intersection using your calculator. We have 3.14619 and 1.14619. And then for this point, we have 0.15859 and negative 1.84141. So those are the coordinates of my points of intersection. Now, since we're going top down, we're going to be working with just x's. Okay, so this will be, we're going to be focusing on our limits of integration. This will be a, where we're starting from, and this will be b, where we're ending at. Okay, so this is x and this is y. Now to apply this formula to this situation, we're going to first of all put in our limits of integration. So we're integrating from, the lower limit is the smaller x value, 0.15859, and the upper limit is 3.14619 times, now f, remember for this formula, g is less than f. Either g is to the left of f or is beneath f. Since we chose to slice in this direction, like this, what's on top, what's on the bottom? F is on the top and g is on the bottom. Okay, so let's label our functions too so we know which is which. This function that's curved right here, this is our logarithmic function, ln x. And then this function down here is going to be our linear function, x minus 2. So if we apply the formula to this situation, the function on top is a logarithmic function. So ln x minus the function on the bottom is the linear function, x minus 2. Now you have to be careful here to put this in parentheses, so you have a error with the sign, and then that dx, that will give you the area. All right, so let me should give you a visualization as to what's going on here. All right, so you have the two functions, the logarithmic function in blue and the linear function in brown. So what we're doing is we're basically adding up all these infinitely narrow rectangles from our lower bound all the way to our upper bound. That's how we calculate the area. Okay, it's like an accumulation of all those, the area of all those rectangles. So let's take a look at what the area is. So you're going from 0.15859 all the way to 3.14619. Okay, so that's net accumulation of those areas is 1.94 9 square units. Okay? Alright, let's take a look at the B part. So for the B part, it says find the volume of the solid generated when R is rotated about the horizontal line y equals -3. So